Started.
Okay.
Okay, we're live.
All right. Hello, everyone. Welcome to the Wikimedia Tech Talks series. Today, we have Dan Andrescu, who is a senior software engineer at the Foundation in the analytics department, telling us a little bit about what's going on in the analytics department. What is it that they do there? I am really curious personally as to what is the work they do, and I'm really excited to hear him tell us a little bit about that. And if you have any questions, please use IRC and the Wikimedia Office channel and direct your questions at me, and I'll make sure to pass them along to Dan. And this is just a quick early announcement. Next month, we're going to have Alex from SRE. He's going to talk about the deployment pipeline. All right. I'm going to start this and let Dan present. Dan, you're all good to go?
Yes, I was just launching it and my computer kind of like hangs in there for a second while I'm launching it. Everything good, clear? You can all see the slides? Hello?
Yes, we can see the slides.
Yes,
Okay, good, great. Cool, so welcome. Whether you know a lot about how data flows through our system or are completely confused about what streams and lakes and clouds have to do with anything, you have come to the right place. I'm going to take you behind the scenes and show you how we see our data. Want to have some fun and just basically, yeah, let's look at what it is that we're doing back here. So mostly we maintain about 111 hosts. These have access to 2.4 petabytes of distributed storage. And together this is about 1/10 of WMF resources. So I think WMF has something around 1,300 hosts and 15 petabytes. We're a team of 6 engineers and a manager. 2 of us are site reliability engineers. These guys troubleshoot all the things that go wrong with distributed systems, hardware failures, security upgrades, rolling reboots. They're amazing at reading logs, like the best. One of us streams in Scala and does massive distributed joins on skewed data for breakfast. I'm going to show you some of that later. And 3 of us are getting really good at reading logs because that's basically all we do. The 3 of us have more of a front-end development background, and we work on some of the UI tools, but also a lot of the layers in between have front ends. Like there's 5 layers of front ends, so we got lost in there somewhere. Yeah. And our wonderful manager keeps it all together while also in her spare time hacking bot detection and differential privacy algorithms, which is great. So on top of all the infrastructure, we build and run systems. There's 5 different kinds of systems. I've got them kind of cataloged here. We handle lots of data coming in. So we've got Kafka, Hadoop, et cetera, that handle that. We aggregate and sanitize it, a bunch of custom code that does that. We serve slow answers to really big questions with Hive and Spark. We give fast answers to questions that are asked frequently with our fast query systems. And we make pretty dashboards and graphs and things like that. Most of these systems are out of the box as much as we can handle, and we integrate them with custom code. That custom code is, I'm going to show you a high-level view of it, but it's everything from elegant Python scripts to thousands of lines of complicated distributed Scala and programming. Going into detail on much of this is kind of, yeah, like, we could do it, and there's talks that do this. These are slides, pictures from other slides. Happy to do that at a time in the future, or other folks can. But I wanted to go up a level for this talk and look at high level how the data flows. So I like this kind of corny analogy about water because I like water. If you've seen me running through the rain, you know, streams of data come in. Just like streams. they get filtered through algorithms that get rid of data we don't need, clean the data that we do need, aggregate it, kind of like a wetland does. Now, this part of our system is called refinery because my team refused to let me rename it to wetland, but it's okay, you win some. And finally, the data gets stored in like this big peaceful data repository we call the data lake, where you can have a nice relaxing time floating around fishing for the data that you need. And some of that data gets published for everybody in the world to work with, and you can kind of think of that as evaporating to the cloud. And there you go. I've tied a pretty bow around our whole world here. Yeah, so what's all this water? I'm here to learn about data, not water, right? So let's look at what our platform does. It's basically what we're trying to do is build a platform that lets people ask questions and get good answers to those questions. And that means the most important part of this whole platform is the question, right? Like what is your question? And we all work together, WMF and the movement work together to ask good questions. The strategy processes and these things are results of us asking questions. And so the C team, the researchers, product owners, data analysts, legal, really everybody gets together and tries to find out what we need to know to make to evolve our movement. Once we have that, we can instrument we can add measurements, right? And measurements, we call that instrumentation, like instrumentation panels on planes. And for example, like we maintain code, like the analytics team maintains code that instruments our varnish front ends, and we'll be moving that to Apache Traffic Server when the traffic team migrates the caching layer there. But most of the instrumentation is done by teams developing user-facing products. So you all working on Visual Editor and putting logging code in there, that's most of the instrumentation, most of the logic that does that. And right now we're like in a WMF-wide effort, we're helping improve instrumentation APIs and build more standardized instrumentation libraries. So this all can be easier and we can just get data flowing in. When we have data, it flows in through Kafka, which is a huge distributed streaming platform. We have a variety of different clusters. 2 of them are maintained by the SRE team with a little help from us, used for things like the MediaWiki job queue. Those Kafka clusters may be useful in the future for updating, for example, the complex dependency graph. So when someone edits a template, notifying all the places that use that template that they need to update is going to have to happen via a stream of events, and Kafka can help with that. A big cluster, in the last cluster is used for analytics data. It's a big cluster where we're getting all of our data. So there we're in the modern event platform effort, we're trying to standardize how the data comes in, that it all has sort of standard schemas that evolve in a dependable, stable way on top of it, so that whenever someone comes in and looks at any topic of data there, they know what to expect. Once that data is coming in, we have to sort of handle it, right? So we bucket it, we aggregate it, we clean it, we do all these things that the wetland was doing, and this is the place where we have most of our custom code. So until now, we have a lot of custom infrastructure, and now this is where we have a lot of custom code. So this system is called Refinery. It uses a job scheduler to react to different data. So when data comes in, it sort of sends a notice that it's ready, like 1 hour of data is ready, and we operate on that hour. We aggregate, sanitize, etc. This is a place where, for example, we parse geolocation and user agent information, reconstruct and reshape faulty data, and much more. And we can talk about that more. We want to think about kind of long-term, what is this data, what is it going to do once it lands in a storage system? So one of the first things we think about is long-term retention. We decide if to keep, what to keep, how to keep the data. So we can keep longitudinal data long-term. We can delete after 31 days, etc. We can sanitize, stripping certain fields or making them less granular. Like, for example, the user agent, we don't store that in raw. We get rid of it after 30 days. We parse it and try to determine operating system and browser information, and we keep that around for longer, 90 days. And then we delete that as well and aggregate the data and store that long term. We're investigating differential privacy and other privacy by design techniques. Marcel on our team gave a good talk about this at Strata, and there'll be links to his slides in my slides as well. Now, once we kind of have the data cleaned up, aggregated in a way that we can use it, we have to decide how and where to store it. And that, what we use to decide is how is it going to be used. So if we store anything long-term, if we have huge data that's queried as a whole, so for example, how many editors edit articles that get fewer than 10 page views per day over the past 3 years. Processing that, like an answer to that question, means going over about 14 terabytes of data. And we replicate that threefold, so it's not going to fit on any one machine, right? To query that, basically, we have the Hadoop cluster, which has a distributed file system called the Hadoop Distributed File System, HDFS. And we put that data up there, it replicates it threefold. And so now you have 50-some nodes that have copies of this data all over the place. When you launch a job, we have a resource manager that tries to put your logic as close to the data you're trying to query as possible. So that's HDFS, that's why we store there. If the data is not too complicated, so think like if you have a table, it doesn't have too many columns, like a classic SQL tables, but it has a lot of rows. So billions and billions of rows, but not too many columns, and needs to be queried very fast, then we put that in Cassandra, and Cassandra can serve queries to that data. It doesn't do any aggregation or computation on top of it, but can serve the data very, very quickly. Can index it. Basically, it's a big indexing system. This, for example, hosts data that serves the PageView API. And we're going to go over the PageView API as an example to this whole flow in a few minutes. If we have not super huge, but pretty huge data that's more complicated, so it has many columns, but none of those columns have too many unique values. So for example, like putting all of the user IDs or all of the page, or all of the article titles would be too complicated of a column. So if it doesn't have that, then we put it in Druid, which is a place where you can slice and dice data, really big data, terabytes and terabytes, but not super complicated, super unique data. And there you can slice and dice by different dimensions. So you can hold a property constant, like say the browser, and look at how different metrics fluctuate over the other properties of the data set. So like for a specific browser, what countries, what like mobile versus desktop sites, where is the data being accessed? Druid does this with a clever index that is talked about in other talks. And finally, we have to decide, how do you present this data? Our audience is pretty varied. It includes researchers, both internal and external, people downloading the data and working on public data, product owners in the foundation, the communications team, data analysts, engineers, and community members. So a few examples, like analysts will log into the cluster via Jupyter notebooks, which can use Python to run Spark or Hive and query data on HDFS. So they have full access to basically the big, slow engines there. Community members will look at like Wikistats, which is a pretty UI for top-line metrics. And some community members download huge dumps of analytics data and build tools and workflows on top of it. while like engineers like Eric Bernhardson on the search team will use page view data to train models that improve search results. So we support different ways of interfacing with the data, and the same as our infrastructure, where we try to use out-of-the-box tools. We do the same here. Tornillo, Superset, all of these things come out of the box with lots of value, and we try to contribute to those open source projects. And at the end of the day, though, we have to develop custom code. And I'm going to show you real quick a few examples of these interfaces and how you can look at this data. The most general purpose dashboarding tool we have is called Superset. It basically can access everything on our Hadoop system, all the data sets there. This is showing geo-editors, so a data set that looks at what countries people are editing different projects from. So this is showing like some of the top wikis, English, Commons, Wikidata, and how many editors are coming to those projects, and as well as from what countries are they coming from. This is, so if you want a dashboard, a custom dashboard that gives you something that you want to look at regularly, then this is the tool to use. Tornillo is a place where you go and explore, so you slice and dice data. This, for example, shows traffic for the last 30 days broken down by the browser that is being used. So if you're trying to find a particular pattern in Firefox or something like that, you come here, you can break it down. You can break it down further by versions and all things like that. You can see the dimensions on the left side that you can split and filter by. We have this little tiny tool that does some custom dashboards. This is very useful for kind of canned data sets that provide a lot of value. For example, we released operating system breakdowns and browser breakdowns, and these are widely used over the internet to kind of like determine, we're a big site, so people want to know roughly what's the most popular browser on Wikipedia, stuff like that. And this data set helps them do that. This is the interface I was talking about before, the custom notebooks. You can see here, basically, you're just doing very, very simple Python, like literally putting a SQL statement and calling Spark SQL on it and transforming it to pandas and doing everything, all the data science you want from there. And this is basically running in your browser through a tunnel, through an SSH tunnel, and doing this work on the cluster. So you have the full power of 50-node cluster right here, and you can do anything you want. And finally, this is our community-facing interface, Wikistats. We basically built this so folks can celebrate each other's amazing work. They can find here, up-and-coming projects can find rises in active editors, registered users. They can run campaigns and try to see if it moves the needles, and stuff like that. So this is really focused towards the community and top-level metrics, like stuff that the media cares about and our communications team wants to share. It's all in a nice shareable format. Okay, so that's kind of an overview of our pipeline, and I can walk you through a little example. I talked a lot about page views, so to kind of give you context about this example. There's many other data sets that flow through our system. You can find them all in our docs, or you can ask us, any of us. And but it helps to just give one concrete example. So here's we have the question: how many times does content on our sites get viewed by hopefully human users? It turns out it's pretty hard to determine who's human on the internet these days. Surprised. So we instrumented that by going to our front-end caches. We have a tool called Varnish Kafka that looks at the Varnish log, sends an event to Kafka every time Varnish services a web request, and the data flows into our Kafka platform. We get about 100,000 requests per second, something like that. We get more from other custom events, but that's just page views. Sorry, that's just web requests. Web requests are the raw, sort of unrefined data. Those become page views later, as I'll explain. And we bucket them by hour and store them in HDFS, so that now HDFS has, for this hour, these were the web requests that the Varnish layer saw. now we look at that and we do a bunch of things. First, we check for gaps, right? There could be hardware failures and data loss and things like that. And we check for gaps and we alarm if there's any gaps. Most of our systems have data quality alarms that say, hey, this job didn't do its thing and we have to look into it, etc. Yeah, and we also clean the data, so we take out any raw information like IP address, because we don't really need the IP and we don't want to keep it. We basically want to keep just we keep it for operational purposes, but we delete that after 31 days. What we keep is the location, like the geolocation of the IP. We keep that around. That's useful for analytics, and we parse the user agent like I was talking about before. So we generally make the data easier to use, aggregate it, and then we aggregate it hourly by page title, because also we don't care too much about each request separately. We care more about what articles are being accessed and by what user agents and stuff like that. So we aggregate that. That reduces the size and it allows us to store it long term, free of any sort of privately identifiable information, and allows us to query it faster and move it to the other parts of our flow where it can be used. The decision to keep what we sanitize, what we keep, we basically evaluate privacy risks, whether you can de-anonymize the user, whether you can reconstruct browsing sessions from the data that we have, and then we take action. So we delete raw data after 31 days, refine data after 90 days, and investigate. We're looking at other privacy techniques that we can use to make the data safer, because all we really care about is getting our answers. We don't care about keeping data around for the sake of data. And for page views specifically, the data is of course stored in HDFS and Druid in different forms and showed to different people. But I just wanted to talk about the page view API specifically, because it's relatively simple data. So there's not a lot of dimensions. There's whether it was accessed on the mobile site or whether the user agent was a spider or probably a human. We have few columns and lots of rows, so lots of data. So Cassandra is the right place. We store it there, and it allows us to query it very, very fast. And so we built a very simple Node.js service based on the Node service template, REST-based, using REST-based. And that's basically the API that lets people access data in Cassandra. Yeah, so that's basically the page view API that's used from a whole bunch of tools, a whole set of tools, both internally, using that to combine it with other information, externally to show graphs on info pages of articles on how many page views each page had, and look at project level page views and stuff like that. So, and it's also used in other interfaces that we have, like Wikistats and Dashiki and other places. Yeah, so that's pretty much the page view example. I just wanted to point out one other small thing is there's a tool called Matomo, which if you have sort of a smaller site that gets less traffic, like for example the Wikipedia 15th birthday website that we put up, you just get a little snippet of JavaScript, stick it on there, and you get some automated metrics without a lot of work. So you get like unique visitors and things like that. Yeah, so that's our system overall. I wanted to highlight a few things just to kind of give you context. So if you think in terms of infrastructure, Puppet code, servers, things that are hard for our two SRE engineers to work on, these are the areas where they're doing the most work. So Hadoop and HDFS is just huge. It has a lot of moving parts. Kafka as well. So that's a lot of custom Puppet code. The Cassandra is up there because it turns out Cassandra is very hard to operationalize and to maintain. It's complicated. You have to kind of know exactly how it serves data quickly to tune it properly. And Kerberos is another thing we're working on right now to harden the security on our cluster. So that's involving a lot of work, and that's roughly where the SRE work is going. And the majority of our custom code, so our application logic, is that we write. I think I counted. I don't think we have more than 100,000 lines of custom code, but it's somewhere close to that. So it's not a huge amount. It's mostly tuning things out of the box, but it's not a small amount. It's not like a small code base. It's mostly, some of it is data transformation. We're processing everything from the data sets flowing in to our own data sets that we're importing from MediaWiki. So for example, we scoop all data from all MediaWiki databases and aggregate it and clean it up and present it in a way that's easy to query and ask questions about editorship and retention and stuff like that. To just, like all the data transformation that I mentioned, that's all happening in a big custom code base. And some of that is pretty tricky. I'm going to show you one example at the end of the talk that kind of gives you an idea of distributed programming and why that's a little weirder than normal database programming. And the other, we have a lot of Python utilities that kind of glue everything together and call out to different APIs to delete sanitized data, all that stuff. And our front end, so that turns out is pretty complex. The Wikistats UI has a lot of custom code to make things look pretty and feel good for the user. So that's another bigger code base. And I think one of the last things I want to mention about the overall flow is, tech that you should keep in mind, kind of as you think about how you could benefit from the analytics infrastructure and systems and experience that we have. I was just talking to Subbu, who's working on, porting the JavaScript parser to PHP, and part of that work is testing the results of both parsers to make sure that they match, right? And that could involve a lot of compute, a lot of differences being made. And, that's not at all in any way analytics related, but the compute capacity, so the cluster, could help that problem very much. So things to keep in mind are, the data flowing in through Kafka. So, if you want to react to things in real time, send notifications for different reasons, think about how we compute and aggregate data. You can think about that. Notebooks, if you want to come in to the cluster and run a big job and share the analysis with other people in a friendly Python set of commands, that's available. And if you want to publish data sets, so for example, we're working with Wikimedia Deutschland and other teams internally who want to publish media counts data, so how many times images and videos are being accessed. We don't have very good instrumentation on that, but we do have some data that we're going to put in an API and evolve the quality of the data over time. If you have data sets like that could be useful to you and others, you can think about that. I think for me that's pretty much a victory. So I'm going to declare victory for myself for having gone through and explained kind of the overall picture. Everything that flows through here kind of goes through roughly that thing. There's a lot of nuance. There's a lot of stuff I skipped for the interest of brevity. But if you have any questions so far, I'm happy to take them. I'll tell you, I have after this an example problem that we solve in distributed systems. So I can either take questions now about the overall picture or just go through the example and take questions at the end. I'll wait for Subbu to make the call on that.
Yeah, so I think the stream is at least 30 seconds behind.
Okay.
Yeah, but I did have one question, I think, which maybe others have to. So the picture was pretty impressive. You have a lot of systems in there. And you mentioned how everything starts with a question, right? So I was curious, how does this whole workflow work? I mean, is it, so suppose somebody has a question, how much of it is a lot of custom code? How much of it is kind of, how does it work? I mean, how do you, is somebody sitting with analytics people trying to figure out how to piece it all together, or is there some kind of a language that people write code in? I mean, I don't quite fully follow that.
That's a really good question, and I completely forgot to talk about how we interface with people that use our the most important part, right? Like who this infrastructure serves. Thank you for that. So yeah, basically, when you're formulating that question, that's, like I said, a teamwork effort, and instrumenting is usually on your team. So if you have a product, you're usually instrumenting that yourself because you know your code base, you know all that stuff. We help you in terms of helping you define the schema, and we're working on that process to make it tighter. Like right now, you'd have to talk to legal and a whole bunch of other people to make sure the schema makes sense and it conforms to all the different policies we have. But once you have instrumentation and a schema picked out, then the data starts flowing in, and you can, for the most part, hand it off to us to take in, process in a way that makes sense. We have standard ways of processing this data. We decide together where to store it, like how you're gonna access it, what you're gonna do with it. We can define, so like if the raw data is not very useful, we can define data sets that you build on top of that can be useful, or we can load it pretty much as is with simple modifications into Druid. We have like a direct to Druid. So one of the most common instrumentations is event logging on your feature. Say someone's instrumenting visual editor. Then the events that flow into that data set can go straight to Druid, and they're updated hourly, and you can query and slice and dice right there from Ternillo, the interface to Druid. And so that's all pretty much out of the box. So you don't really have to talk to us at all. If you have data sets that you need more custom attention, then we can help you. To a certain extent, we have a priority list, and you have to get in line, of course. But we can help you shape that stuff and load it on whichever platform makes sense for you to query. Yeah, does that help answer, or do you have?
Yeah, that does help answer the question. I have more, but I can follow up later. Andre had a question on IRC.
Yeah.
He's asking, are there plans to update, redirect, or do something about stats.wikimedia.org, which looks very static and at least for me makes it hard to find things?
Yeah, so this, where's the tool? No, I got lost, sorry. This tool, this is Wikistats 2. If you go to stats.wikimedia.org/v2, you'll see this. We're being very cautious about the quality of it. It's definitely totally okay to browse, but we're just being very careful that it meets all the community expectations that have been built up with the old tool. So the old tool might look static, but it's actually like a collection of brilliant work by Eric Zokta that a lot of people find extremely useful, and they've sort of gotten used to it over the past 12 years that it's been up. So we're displacing that very carefully. And right now this project, this Wikistats 2 project, is in alpha mode. It's going to hit beta sometime in the next few weeks, probably. And after that, we have a bunch of other changes that we want to do over the next year, and it's going to be released next year. But I think when it goes to beta, we're just going to redirect it automatically. Input about that is welcome, of course. I mean, everybody here, I think, uses Wikistats to some extent, so it's all your tool. Like, let us know if you think it's ready to go to this new version and stuff like that. Or we find that feedback useful. Okay. Let's go to
IRC.
another question.
There are no other questions.
Okay. Okay, great. Let's go and take a look at this little example problem, and then I can answer any other questions at the end. Okay. So I chose this because I ran into it, and Joseph, who's the Scala distributed system expert on our team, he explained to me what the problem was, and it was very frustrating for me because I'm coming from like a more traditional database background, and I was so confused why this particular problem happened. And here I'll set up the context. So we import a bunch of MediaWiki data. Let's focus just on the revision table and the comment table, right? So recently, comments have been factored out of revision, and they're now linked by an ID, and we have to join revision and comment together to get those comments, because some of them are useful for the reconstruction we do. We collect all the data together, so when we import, we don't keep each database separate. We just put it all in one place and add a column called WikiDB. That helps us analyze everything together. It helps us do cross-wiki joins and stuff like that, and it's a lot, more helpful for analytics purposes. So when we join those two tables, we're joining all of the revisions with all of the, from everywhere. And the problem is basically that the data is skewed. So a lot of revisions have the empty comment, for example. Let's pretend like, the first couple of revisions have comment ID A and B, and revisions 3 through 10 billion have, comment ID X, which happens to be the empty string. So when you join this table, what happens? Does it just take a long time, or no, it just fails. It just completely burns to the ground in a spectacular fashion. And even though we have a big cluster and plenty of capacity to process all the data, what ends up happening is that you can't parallelize this particular join. And I'll kind of explain why. So the data is skewed. You have many, billions of revisions on one side trying to join to one record on the other side. And when we join, when we join in a distributed system, we use a technique called map reduce, right? So we sort of break the problem down into two steps. First step, we have a bunch of mappers, so a bunch of workers that are looking at a big distributed cluster and going to the data and saying, I want this part of the data. So that's where the filtering would happen, just like you would do map on javascript.map or PHP. And you filter what you need and you send it to another worker called a reducer. And then the reducer does whatever aggregation type work, like you would call reduce in JavaScript, that you take multiple streams from different mappers and you do some work on it, and then you output, and then you combine the output from a bunch of different reducers, and that's your final output. So that's kind of roughly what that looks like. You have a bunch of data distributed all over the place. You have mappers that know how to fetch it. They go in and they find rev comment ID X and comment ID X, and they know that this is going to be a join. So they take rev comment ID and comment ID and hash it by the number of reducers and send the result, send the row to the reducer that the hash maps to, right? So like you're trying to distribute a big data set of millions of records into n reducers. You're going to hash mod n, let's say, so that it lands on one of those n reducers. And the problem that you run into with skewed data, so when you have lots and lots of repeated values, is that all of the comment ID X will hash to the same reducer. And that reducer just burns to the ground. It just, it can't. And if you have 100 records, it wouldn't, right? It would be fine. If you had 1 million, 10 million, it would be fine. The problem is it has so many records that it can't even swap them out to disk as it's processing them, because that operation is too slow. So think about if you have 10 billion records and it takes 10 milliseconds. So if you have just 1 billion records and it takes 10 milliseconds per record, that's 4 months of computation. So if you can't, for example, like if you thought, hey, this is kind of dumb, like I'm just hashing the same value to the same reducer, why don't I set up some server somewhere, like a very fast lookup server, like a Redis server, where I tell it, I just keep a tally of how many times I hashed X to a particular number. And when it gets to like 1 billion or however many records one reducer can handle, it does like a little collision detection and starts hashing to a different reducer. Well, that that conversation over the network would take a few milliseconds, and if you add those milliseconds together, you end up with like months of lag. So with this size data, you literally can't do it. So what do you do? How do you solve that problem? How do you take the load off of? How do you deconcentrate that load? The very ugly and not at all generic solution. There is no generic solution that we know of, that I know of. But one way you can approach it is you can sort of add a fake ID to one side of the join that you randomly assign a number between 1 and k, where the k is like some constant that you magically came up with that works for your cluster, whatever your cluster size is. And then that's on the side that has the many duplicate IDs. And then on the side that you're joining to, you want to duplicate those IDs with that new fake ID so that there is a target for all the joins. So you duplicate that k times. You randomize 1 through k values for fake ID over 10 billion records on the left, on the revision side, and you assign you multiply the comment ID x field by k on the comment side. So now when the join happens, all of the random 1 through k values from revision will find a join on the comment side, and it'll be the same value because you're just duplicating the comment text. And when it hashes it, instead of hashing just comment ID x, it now hashes fake ID 6, comment ID x, fake ID k, comment ID x. And those are all different hash keys, so they'll get evenly distributed. So now you've managed to evenly distribute your work over your reducer cluster, and you don't burn one of them to the ground anymore. So yeah, any questions about that? Did I lose anyone on that? I don't know if I did a good job of explaining, because like if you just learn something like that, you don't always do the best job of explaining. So I'm happy to go over something again or fill in a gap.
Can you explain why you picked this example? What you're trying to illustrate with this example? Maybe that will help a little bit.
Yeah, so this is something we do. We ran into this problem when this refactor happened. So what we do, let me back up a little. So we put together a data set called the MediaWiki history data set. That's taking all editing metadata from all the databases, looking at the logging table, finding where users changed their name, where articles changed titles, where users were blocked and unblocked, pages deleted and restored, revisions reverted, all of the different things that happen on the wikis, and we put them all in one table, literally like one table with many columns that explain everything that happened to that revision and give context. So for example, one row would have the number of edits that the user making that action has done up to that point in their life. It would have the name of that user at that point in time and the name of that user currently today. That's kind of what the data set looks like. And we build this by doing a complex set of aggregations on top of the MediaWiki data. So when there's a refactor in the MediaWiki schema, that affects us pretty deeply. And this was one of those examples where we had to join to the comment table all of a sudden, and not so much now, but especially in the middle of that migration, we ended up seeing a lot of skewed data because not all of the comments had come in, so a lot of them were null. A lot of the comment IDs were null, not migrated yet. And we hit that problem, and I wanted to illustrate kind of the difference between working with big data and how that can have unexpected nuances versus if you're just doing a join on a couple of big tables in SQL, it might just take a long time, but it's not going to run out of memory or crash some particular worker because it's just, churning over it and swapping to disk when it needs the join and stuff like that. So that's why I picked this example.
Sounds good. That's helpful. Thanks.
Sure. So we keep good docs on all of our systems and infrastructure and procedures. And if we don't, keep us honest and let us know. We'll update the docs. But feel free to visit them. They're on wikitech/analytics. And yeah, thank you. And ask me anything.
I will look on IRC.
I missed the very beginning. Is this recorded?
I think so.
Yeah, this is recorded and streamed.
Oh, awesome. Okay. No, this is very helpful. And will you share out the slides as well?
Yeah, I have. I noticed that on Commons there are usually PDFs, but I have the slides with the notes as well. I'm happy to share that because I think that's where most of my talking is. So I'll do both.
Awesome, thank you. I'm going to further share this with other people in product.
Great. That's awesome. Yeah, I hope that it helps. And I thought there was we usually talk about more specific systems or more specific algorithms. So I thought this would be an interesting overview.
Yeah, no, seeing just the high level view and how it all works together is super helpful. So I'll make sure my team sees it definitely as well as other people.
Thank you very much, Kate. Yeah, if you don't have questions, go have the rest of your day. Go have fun. We're gonna meet the new CTO in like a few minutes, right? So.
Wait, what?
There's a meet and greet with one of the CTO candidates. Sorry, not the new CTO. One of the CTO candidates. I hope I haven't in someone's mind by accident there. Yeah.
All right. Thanks, Dan. And
Thank you.
okay.
Thank you. Thank you all. See ya.
Bye.
Thanks.
Thanks, Brendan.